Pode começar.
Obrigada. Welcome everyone to today's seminar. It's a pleasure to introduce Gabriel Caminha, who is a postdoc fellow at the German Center for Cosmological Lensing based at the Max Planck Institute for Astrophysics in Germany. Gabriel obtained his PhD in 2013 at CBPF, Centro Brasileiro de Pesquisas Físicas, no Rio de Janeiro. From 2014 to 2017, he was a postdoc at the University of Ferrara in Italy, working on strong gravitational lensing, modeling of clash and the Hubble frontier fields clusters. From 2017 to 2020, he held a postdoc position at the University of Groningen in the Netherlands. Gabriel is an expert on strong gravitational lensing by galaxy clusters. His work consists of using strong lensing in its full potential to explore a wide range of subjects, for instance, the structure of galaxy clusters, predictions from cosmological models, and the high redshift universe. Thank you so much, Gabriel, for accepting our invitation. You may start when you're ready.
Okay, thank you. This is actually my pleasure to have the opportunity to talk about my work here with you. And of course, this work is done in collaboration with several people. Some are listed here, but of course, many others. And in this talk, I will talk about the cluster strong lensing, and I will be focusing on the modeling of the mass distribution of some of the systems, and also we'll mention a little bit the science of some background, but strongly lensed galaxies. And so I think you all know that very massive objects in the universe, if they have enough mass, they are capable to deflect the light of background galaxies, and that's the so-called gravitational lensing. And the object that acts as a gravitational lensing can be stars, galaxies, or in my case, in my field, galaxy clusters. And we know that there are different regimes in gravitational lensing. And just to mention, for example, the weak lensing regime is when you have just small distortions on the image of this background galaxies. We cannot detect individually this weak lensing effect, but statistically we can measure this effect. But when you have a very good alignment between the observer, the lens, and the background galaxy, we enter into the so-called strong lensing regime. And this is, at least for me, it's extremely interesting because in this regime, we have the creation of multiple images from the same background galaxy. And these multiple images are very important because we are going to use these positions to constrain the mass distribution in the very inner region of these clusters. And also we have the distortion of this strong distortion of these background galaxies, creating this the so-called gravitational arcs. And in addition to that, we also have high magnification factors of the background galaxies. So basically, we can magnify the total flux of these background galaxies by factors usually 5 or even much higher, 100 or even more, depending on the positions of these images. And this effect is extremely interesting also because it does not depend on any assumption on the physics, on the baryonic physics that is happening in the lens, or even on the dynamical state of the lens. So we sense, and we are sensitive only on the total mass distribution of these lenses, which makes it extremely powerful to measure the mass of the lenses. And also, since these are in the case of cluster lenses, these distances that we have, they are all cosmological distances. So we also are sensitive to the geometry, to the background, to the underlying geometry of the universe. So, and then basically we can study this several aspects. For example, we can go and measure in details the mass distribution of clusters We can measure, for example, the inner slope of the dark matter distribution, the abundance of substructures in these clusters, and compare to predictions from N-bar simulations, for example, from the CDM cosmology. We can also probe directly the background geometry of the universe, basically the cosmological parameters, omega mater, omega lambda, and in the cases where we have time delay measurements, we can even measure the expansion rate of the universe. And again, as I mentioned, we can use these objects as gravitational telescopes to study the background galaxies. But to do all of this very nice and interesting science, what we need first is to have a good description of the lensing of the cluster. And to do this, we have to have, of course, very good data. And but only high resolution photometry, basically from HST, is important, but it's not enough. And we have to rely also on very good spectroscopy in order to confirm these multiple images that I have mentioned, and also to identify the galaxies that belong to the cluster. And of course, this the spectroscopic data is also extremely important to remove any bias, or at least to minimize any bias on the lens model, because in this case we have no kind of misidentification of multiple images. And we also have, when we have the redshift of this background galaxies, we remove the degeneracy with some parameters of the lens model. And also my talk, I'll just divide my talk in these two parts. First, I will talk about the mass distribution of the clusters, and also how to measure the background geometry of the universe, use cluster strong lensing. And in the end, I also mention one application of lenses as gravitational telescopes. We are lucky because nowadays we have very beautiful data, and this data is there. It's all available. Basically, from the imaging part, we have had a lot of HST programs. This, for example, these three programs: the Clash Lensing Supernova Survey, Clash, the Hubble Frontier Fields, and the Reionization Lensing Cluster Survey. These are three large HST. These are HST treasure programs that have observed around 70 clusters at this redshift range, kind of intermediate redshift, using over 1,000 orbits of HST, which is a lot of data. But this is photometry, and again, we have to have also spectroscopy, and there has been a lot of efforts from the spectroscopic part. I don't know, around 7 years ago, we have the Clash VLT, basically using VMUSE to observe around 20 Clash clusters. And after the GLASS, which is a program using HST GRISM, so it's a little less spectroscopy. But nowadays with MUSE, with the MUSE instrument that I will talk a little bit more later, this field is basically being revolutionized because of this instrument. And what is extremely interesting is that in the very near future, there will be JWST data on cluster strong lenses from guaranteed time, and also early science programs that will observe cluster strong lenses with HST. And also recently, we are very happy because some geo programs to observe cluster strong lenses have been approved. So this will be also some kind of game. We will also add a lot of good data on this field. And here, just to show you the data a little bit. This is the cluster MAX 1206. It belongs to the Clash survey, and it has been, of course, observed by HST in several different filters from 0.4 to 1.6 microns. And here, the red galaxies, they all belong to the cluster. Most of them, they belong to the cluster. And the cluster is at redshift 0.4. And for example, as I said, we have, in the strong lens regime, we have the creation of gravitational arcs For example, this here, very obvious system that we use to constrain the model. The mass, we use this to measure the mass distribution of the cluster, and this is a very obvious gravitational arc. Here we have actually 3 multiple images from the same background galaxy. This is one image, and here you have 2 images that they are in reality merging into this giant arc, and this is an obvious multiple image system behind in this cluster, but they are not so obvious. Actually, this is an easy one, but just to show you this, again, these are 3 different multiple images that it's, we can say they are from the same source because they have the same, looking only on the photometry, we see that they have the same shape. The parity is also in agreement to what we expect from lensing, and they have same morphology, same colors, but we actually need confirmation because, okay, this is obvious, but we have others that are not so obvious in the photometry, and the only way to obtain confirmation is to have spectroscopy on these systems, because with spectroscopy we can measure the redshift with very good precision, and we can just be sure about these systems, and again, MUSE is the best instrument to do this kind of science because it's an integral field unit with a large field of view, 1 microminute. So we can, with 1 or 2 pointings, you can easily cover the entire core of the cluster. And it has a good wavelength coverage with a very good spectral resolution. And here I'm just showing the MUSE spectrum of these 3 multiple images. And you see that we confirm the redshift very, with high precision. And we also confirm that they are indeed the same object because the spectral features, they are all the same. And we have the redshift value that is also an important quantity that we will later on use as inputs to our strong lens models. So I will now talk about the first part of the talk about mass distribution in clusters. We have several reasons why we want to study mass distribution in clusters. And first, I think the main one is because we know that the lambda CDM model is very good to predict, to describe the large scale structure of the universe. But when you start looking into small scales, we start having some problems with the lambda CDM model. For example, we have the dark matter inner slope problem that from numerical simulations, we expect to have, for example, a Navarro-Flink-White profile, which gives you a specific slope. But from observations using strong lensing, we see that this the inner slope of the dark matter profile is shallower than what we expect from lambda CDM simulations. Another issue when looking into small scales is the abundance of substructure of massive substructures in the core of the clusters. For example, this is just to mention a recent paper where the authors, they have measured this quantity, which is the probability of finding galaxy strong lensings inside the cluster. So it's not the probability of finding giant arcs, but probability of finding galaxy scales like this inside the clusters. And these cubes here show the observations, basically observations using different samples, actually, from using samples from CLASH, from frontier fields. And the comparison with simulations, with N-body simulations. And these simulations, they are not simple, they are really complex and up-to-date simulations that include baryon effects and several effects. And we see that we have this huge discrepancy between simulations from the CDM scenario and the observations of more than 1 order of magnitude. So that's why it's important to know in detail what's the mass distribution inside these clusters in the very small scales. And this is what we have been doing, and to do this, we again here I'm showing the spectroscopic data that we have on Mars 12/6. This is just an example. And here, each point is a galaxy with spectroscopic confirmation as a function of time, of look-back time, or the redshift. And here in red, you have all the cluster members, and blue points, they come from VMOS, basically using slit spectroscopy, standard slit spectroscopy. And the magenta points show the confirmations using MUSE observations. In this figure, you have all these magenta crosses. They are multiple images from different families. And these are basically the inputs that we use in our strong lens model, in addition to the galaxy, to the cluster members. Here, now I'm showing the actual MUSE data, the actual MUSE coverage in this field of view. So the MUSE data is relatively deep here. It's a mosaic of 3 pointings, and that goes as deep as 8 hours in these regions. But overall, it's a 4-hour coverage in the outskirts. And this data is crucial to confirm all these background galaxies that are used as constraints to the model. And just to mention that in order to model this the mass distribution, we assume a photometric model to describe the mass distribution of the cluster. We first use the smooth components, diffuse components that account mainly for the dark matter, plus cluster members. And we also use different profiles, use either isothermal profiles or generalized NFW profiles to describe the dark matter that I will mention later on. Okay, and just to show again how just to show the great improvement that we have in terms of strong lensing, in terms of model constraints when you have MUSE. Here in the y-axis, I'm showing the number of spectroscopic confirmed families of multiple images. So basically here we have model constraints. And here is the cross-section, the magnification cross-section. And the points, they show the number, here again, the number of families of multiple images that you have before MUSE, and arrows shows the improvements that you have in terms of constraints when you have MUSE observation. So you can easily add, double or multiply by larger factors the number of model constraints in clusters when you have MUSE data, which is very good because you start having a very clean sample of multiple images. So we have very clean, strong lens models. And this is the sample of clusters that I have been working on. They are from the MUSE observations. They come from different programs, and also archival data, and also programs from me and my collaborators. I have this 7 clusters, and they have different redshifts, and they also have different dynamical states. For example, Max 416 is a very prominent system, very prominent merging system. So the mass distribution is very elongated and very complicated to model. And you have also some very regular clusters that I show here that they have only one BCG, and they have very simple mass distribution when modeling. Again, just showing again the MUSE data on this cluster, now Max 1931. This is the MUSE field of view. And again, we confirmed several multiple images. Here you have, for example, this multiple image of family 5 shows a very clear Lyman-alpha emission, and this other system, family 1 show clear O2 emission. And sometimes it's much easier to detect on the spectroscopic data, on the MUSE data, than on the HST data in this cutout here. But MUSE is important not only for the multiple images, but it's also extremely important to identify the galaxies that belong to the cluster members. Here, in this other field of view, all white circles are cluster members that have spectroscopic confirmation from MUSE. So we know that they are at the same redshift of the cluster, they belong to the cluster. And we use this information together with the HST photometry to select the cluster members outside the MUSE field of view. For example, use a combination of red sequence and photometric redshifts to select the members that are not in the spectroscopic in the field of view of MUSE. Sorry. Okay. And then we have the two inputs for the strong lens model. We have the multiple images, and also we have the cluster members. So, and then we do auto modeling, and we obtain the mass profile. Here I'm showing the 1D, the total mass from the strong lens model, and here these lines are basically the position of the multiple images. So the positions where we have strong lens constraints, and in this case, the blue and the magenta regions are two different models using two different parameterizations of the for the smooth component, for example. And we see that not only for the total mass, but also for the density profile. This is the density profile as a function of the radius of the cluster. The two parameterizations, they have very similar mass profiles, so telling us that our models, thanks to the constraints that we have, they do not depend on the parameterization that we use, at least where we have the strong lensing constraints. And when comparing to previous works, we see that this is a great improvement, because for previous works that have used it are very, of course, because of the data at the time in 2015, they didn't have the spectroscopic coverage that we have now. They had a much limited number of strong lens constraints, and most of these with no spectroscopic confirmation. And of course, the mass models from this using this data is much different from what we have, but somehow they agree where both models have the strong lens constraints. Okay, it's fine, but the good is that we also go much deeper into the inner regions of the core of these clusters, like 30 kiloparsecs. We have good mass estimates down to 30 kiloparsecs of these clusters. And of course, this is for the single cluster, max 1931, but I have done the model for my entire sample of 7 clusters. And here I'm just showing the comparison of the mass profile of my entire sample. And of course, each cluster here, they have different size, they have different masses and also different sizes. And in order to compare all the mass, the mass profile of all these systems, we have to scale the total mass and also the size of these clusters. And to do this, we use proxies to the proxies to the virial mass, like M and R200 from independent measurements. And what we see when comparing these rescaled masses, we see that they all have very similar profiles here on the total mass, not only on the total mass, but also on the density profile. Although these clusters, they have very different redshifts from 0.2 to 0.6, and also the mass range is somehow large. And it's interesting because this self-similarity, it's a prediction from simulations. And we here for the first time, we're observing this self-similarity down to something like 10% of R200 which is very similar to, which is a proxy to the virial radius. And here is the result from using simulations only, and you see that this self-similarity is present in simulations, and we confirm with observations. One interesting thing to note here is that this cluster here, which is the one that kind of deviates the most from this self-similarity, it's max of R16 that I mentioned before, which is a merging cluster. So probably this is why it deviates from the overall trend. It's it's a cluster that's still merging, and it's not visualized, but at least the mass measurement that I have, it's very precise here. Okay, so now we have this kind of nice sample of clusters with good strong lens models. Something that we can also do is to probe the background geometry of the universe. And this is possible because, again, the distances, they are all cosmological distances. And the equation that relates what we observe and what is the intrinsic of the intrinsic positions is so-called the lens equation that I show here. And this lens equation depends on the mass of the gravitation of the lens, and also on the cosmological distance. These are the angular diameter distances. And okay, we have some degeneracy between the mass and this ratio of distances, but once we have different multiple images at different redshifts, and of course we know the redshift of all these multiple images because we have the best data available, we can break this degeneracy. And in the end, what we are sensitive to this quantity that's so-called the family ratio. This is our kind of cosmological ruler that can use to constrain cosmology. And in this case, you are sensitive to, again, to the background geometry of the universe, basically omega matter, omega lambda, and the equation of state of the dark energy. This methodology has been explored before, and only in single clusters. And what I'm showing here is just the intrinsic degeneracies of this quantity as a function of the cosmological parameters, just as reference for, in this case, for a CPL model where the equation of state of the dark energy varies with redshift or with this. And these are just theoretical. These are the intrinsic degeneracies from this quantity. But looking to real data, and this is now the constraints using real data, using the cluster Abel 1063, which is one of the clusters I have shown before. We say that this is not so trivial because we obtain the exact same degeneracies that I expect from for this quantity, and this is basically telling us that we are getting the mass correctly, and we are sensitive here to the cosmology, because if we have some issues with our mass measurements, these curves would be in completely different places. And even our sensitivity, and we see here that we are very sensitive to W, and also we can constrain omega matter. We are not so sensitive to omega lambda, because basically here any value of omega lambda is allowed. And the first parameter of the evolution of the equation of state with redshift is also not, we are also not very sensitive to this quantity, but at least you can see here in the density part, we follow correctly the expected degeneracy. Okay, this is very nice because we can use one cluster to probe cosmology. We are not so sensitive to WA and also not so sensitive to omega lambda because of the intrinsic degeneracies. And this is, again, for about 1063, that is a regular cluster with it's a very massive cluster. It has a lot of multiple images, which means it has a lot of model constraints. But what we can do now is to combine the probes from different clusters. And this the combination. Here, I'm just focusing on the clusters with kind of regular mass distribution, because it's easier to constrain the mass distribution. We have only a few components describing the mass distribution, different from merging clusters. For merging clusters, you need a lot of mass components, And we introduced a lot of free parameters, and these are very hard to model. And you have also additional general synthesis between these additional mass components and the cosmological parameters, but at least focusing only on the kind of regular, or focusing on the sample of clusters with regular mass distribution. These are the kind of cosmological constraints that we have. Here, each contour comes from one different cluster. This is only the 68% confidence level. And again, for Abel 1063, which is this very massive, and this cluster with a lot of constraints, we have these nice constraints on the parameters. And for the other clusters, they don't have as many constraints, but they also have some kind of good, we can use them also to measure. And of course, here on the right, I'm showing the combination, not only the 68% confidence level, but the 1, 2, and 3, the equivalent to 1, 2, and 3 sigma. And you can see that we are extremely efficient to constrain W, the first parameter of the equation of state for the dark energy. And we also have good constraints on omega matter here. And okay, so once we are now happy with all these models, with this, we know that we can describe very well the mass distribution of the cluster. So if we can describe the lensing effect, can also recover with very good precision the magnification factors, the properties of the background galaxies. And this is what I will be talking in the next 10 minutes. Actually, I will just talk about this, the MUSE deep lens field on the cluster Maxwell 416. Maxwell 416, it's a Hubble frontier fields cluster, so it has very deep HST imaging. And here it's the HST imaging. And again, this is now the cone plot for Maxwell 416. Again, all these points are spectral confirmations, and the magenta are the confirmations from MUSE. The great benefit of using gravitational lenses to study background galaxies is the magnification factors that you have. Of course, we are very confident on our magnification factors because we have a lot of strong lens constraints. We have accurate strong lens models, and it's extremely useful because in terms of signal to noise, basically the signal to noise will increase with the magnification factor directly against the exposure time that is the square root of exposure time. So if you want to increase your signal to noise, the most efficient way is to have a lens in between you and your background galaxy. Otherwise, if you want to increase the signal to noise on a galaxy that's not lensed, you need a lot of telescope time. And talking about the precision on the magnification factors that we obtain from our strong lens models, this is just a simple simulation, but it gives you the message. Here I'm showing the uncertainty on the magnification factors from the models as a function of the magnification of your background galaxy for 3 different models. One, the blue model, is kind of the model it's just a simple simulation when you would have no spectroscopic information. So for magnifications of 10, you easily reach errors of 50%. But as you include spectroscopic information on your model, you really put down your uncertainties on the magnification factor. So that's why it's important to have these good models, and we can probe in detail the background galaxies only because we have these very accurate models. Okay, the deep lens, the MUSE deep lens field on Maxwell 416. It's a program with MUSE that has observed during 17 hours one field of view. I'll show this field of view later. This cluster, it has a flux element of 10 to minus 19 in CGS unities at this wavelength, which is very deep. This is the observational. This is not accounting for lensing. And if you consider the region with magnifications of around 8, or here I'm showing the region where we have magnification factors above 10 in this field of view, if you would, and this survey in this region is equivalent to basically 1,000 hours of MUSE on a blank field, on a field with no lensing. So it's basically impossible to reach such depth not using gravitational lensing. And okay, the first paper describing the survey and just giving highlights on some science is described. It has been published recently in this paper here, and again, but of course this is very nice. But the only thing that happens is when we are in lens fields that the real area that we are probing is much smaller than the area that we observe. However, in reality, this is not a problem, because in the end, we want to explore the faint galaxies and the distant galaxies, because basically these faint galaxies, they constitute they are the most common galaxies in the universe, mainly if you go to high redshift. And this low mass, and given the number, since these are very numerous galaxies, they basically dominate the star formation at high redshift, and they are thought to be the main sources of reionization of the universe. So then we are, okay, it's fine, we're observing a very small area, but we are observing this population that is the most common population of the universe. And this is the field of view of the MUSE deep lens field here. So basically we have 17 hours of MUSE on this single area. We also have additional archival data from other programs, but focusing only on the deep exposure that I'm showing here. We have actually updated the strong lens model. We have an unprecedented number of model constraints for Maxwell 416, almost 200 multiple images to constrain the mass distribution here. But if looking into the background galaxies, and actually these are all multiple images, we can also see in details these objects. And of course, we reach very deep intrinsic magnitudes, and also thanks to the HST in combination with the magnification factors, we can measure sizes down to 3 parsecs in some of these systems at redshift 3, 4, 5, which is extremely interesting. And for example, most of these high redshift galaxies, they all show clumps, different clumps, and we are sure about this clumpiness because of the multiplicity. We see the same pattern in the different multiple images, and they all show clumps of star formation. And in some cases, we can even resolve spatially these clumps and see that they have different colors, perhaps different star populations inside the same galaxy at redshift 3, for example. This is just a comparison of our sample of background galaxies. Redshift, the size of the circle shows, indicates the redshift. And here is from the MUSE deep lens field. And here are galaxies from the field, from the GOD survey, and from the GOOD survey. And again, here we go to extremely small. We can detect extremely small clumps here in this galaxy at redshift 1, and find details of a galaxy at redshift 6 here and redshift 3 here. Okay, we have a lot of interesting sources here. I'm going to talk about only one because we have, of course, not time. And this is the so-called ID14. ID14 is, again, a multiple image. It's a system of multiple images. And here we have 1, 2, 3, 4, 5, and also actually there is a 6th image in another region. And we can resolve it. It has 2 camps here, and it is highly magnified. It has a magnification on the 40, but with a good error bar, thanks to our model. And the size of these camps is around 30 parsecs. Again, we are observing 30 parsecs at redshift 3.2, and it has a relatively high star formation rate and mass of 10 to 6 stellar masses. But also, what is interesting is when looking to the spectrum, this is the MUSE spectrum. And since we have different multiple images, here we are stacking the spectrum of these 3 multiple images, which give us the equivalent of 51 hours of exposure time. And we can detect all these lines. And it's very interesting. The system is very peculiar because it has all these ionization lines, which is telling us that this system has a very strong UV, very strong ionization, but it has basically no Lyman-alpha emission arising from it. But these lines, they are expected to be present in the case when we have a Lyman continuum photons. I mean, a very UV photons. These are photons with higher energy than 900 angstrom leaking, but we observe no leaking of UV continuums because we have also UV imaging here, and there is no detection. But what's interesting is that the Lyman-alpha, which is not detected arising from the clumps, it is detected arising in a different region, but again, it's same redshift, but with an offset of around 1 or 2 kiloparsecs. And it's intriguing because we expect in this galaxy to have Lyman continuum radiation escaping because of these ionization lines. The Lyman-alpha, which kind of would indicate some paths where the Lyman continuum would escape, is not present, but it's present here. And in this case, for example, the interpretation is that maybe there is a tunnel of UV continuum photons escaping, but not in our direction, but in the transversal direction, that it's powering the hydrogen gas in the outskirts of the system in this region here. And this is still something to be fully understood, but luckily this system, specifically the system ID14, will be observed by JWST, by one GTO program, one of the GTO programs. And so with this, we will be able to, at least the GTO program, they will be able to probe the optical lines like H-alpha, oxygen 2, in the rest frame optical. So they'll be able to trace very accurately the star formation of this system. And this will kind of give very interesting hints on how the star formation is happening here, not only from the photometry, but using these optical has-frame optical lines with JWST. And okay, this is just my summary. We have built this sample of strong lens models with very good data. So we have a very we have very precise measurement of the mass distribution. The first thing that we that the mass distribution of all these clusters, they are very similar, which is actually a prediction from N-body simulations. And we can also probe the cosmography, the background geometry of the universe, by combining the probes from different clusters. And this is a great potential. It has a great potential. And okay, we are opening a window. We have opened the window to these very faint objects at our intermediate redshift, where we can basically, in some cases, really resolve especially the star population in some cases, and confirm several galaxies at redshift 5 or 6. We can resolve scales down to 10 parsecs at high redshifts, which is extremely interesting. And we have some interesting systems that they have indications of the Lyman continuum photons to be escaping, but we do not observe. So this is indicating that that there are some porosity on the interstellar medium where the UV photons can escape. And of course, with JWST, we'll observe the optical rest frame of these galaxies, of these redshift galaxies, when we'll be able to probe specifically the star formation with high precision. And of course, all these lessons that we learn at lower redshift 6, we can are extremely useful for higher redshifts where the reionization of the universe has occurred. Yeah, and that's all I have to say. Thank you all for your attention.
Thank you so much, Gabriel, for your very exciting talk. For the people following the talk on YouTube, thank you for joining us. If you have any questions, please post them on the YouTube channel chat. We'll be back next week with a seminar on galaxy metallicity scaling relations in cosmological simulations. Goodbye. And now we go to the breakout rooms.